everyone. So this is going to be the last video on Newton's laws of motion. Like I said, this is an overarching thing, so we're going to be constantly coming back to these laws. Um, so let's just move on to the very third law. Now, this law is actually a little bit different from the first two. If you recall, the first two laws, Law 1 and Law 2, were basically talking about the forces acting on a single object. Newton's third law, however, talks about the interaction between objects. And it tells us pretty much how the forces are related. Now, before I say what the law is, let's consider the case. Let's say that a man is standing on a skateboard. Both him and the skateboard are at rest. He takes a basketball and throws it forward. We want to know, well, does the man stay still or move? You can actually test this yourself, and you'll find that depending on how heavy the basketball is, of course, and how heavy the friend is, you will actually see the person move when they throw the ball. And in particular, the person is going to be thrown backwards. So by the man throwing the ball forward, he gets pushed backwards as well. So this leads us to the third law, which basically says for every action, there's an equal and opposite reaction. That when the man throws the basketball forward, the basketball throws the man back with the exact same force. And that's the important aspect, that the forces between the two objects are going to be identical. I usually call this the law of action-reaction pairs because it basically talks about this idea of the symmetry between an object exerting a force on something and then that something exerting the same force back onto it. One thing I want to point out is that if you recall, the whole idea of Newton's first law was saying that if there are equal and opposite forces acting on an object, then the object will be in equilibrium and they cancel each other out. Some people will mistakenly apply this with the first law and say that if there's an action and a reaction that are acting on an object and they're canceling each other out and they're equal and opposite, then they should immediately come to rest and be in equilibrium. It's important to note that that's not always the case. When we talk about action reaction, it's important to remember that the action and the reaction are sometimes acting on separate objects. For example, if we have two blocks and they're connected by a spring, regardless of their mass, the spring is going to exert a force onto it that's equal and opposite. So the spring is going to exert a force onto this object, force F, and this spring is going to exert a force on the second object in the opposite direction of the exact same force. Now, if I look at it on a whole, then yes, these two forces will end up canceling each other out. But if I just look at one of these objects, like the box on the box on the left only feels one of the forces. Let's say call it the action force. It does not experience the force going to the right, only the force going to the left. The box on the right, on the other hand, experiences the reaction, the force pushing it to the right. It does not feel the force to the left. So as far as the box is concerned, there's only one force acting on it, either the action or the reaction, not both of them. But it is true that if we have a system where there is going to be two people applying a force onto it, like maybe a person standing in a box pushing against a wall, then because the person and the box and the wall are all being considered as one single object, then the whole idea of you applying a force and then it applying a force back onto you, then they will end up canceling out because you're on the same, you're in the same scenario, the same system. I'll go into a little bit more detail with this when we start talking about objects and system in the multi-mass section. But that's kind of the idea, that you had to pay attention to whether or not this idea of action reaction is occurring on this in the same object, or if it's acting on two separate objects. So yeah, I'll mention that a little bit later on. But yeah, this law basically says that every time objects interact, if something is exerting a force onto it, then it exerts the exact same force onto you. This is basically how everything pretty much works. It's how planes fly. It's how we can swim. It's how we can walk. If I think about a person walking, basically, in order for a person to walk forward, what they need to do is push on the ground going backwards. That pushing on the ground actually results in the ground pushing them forward, giving them that forward motion. If they push on a block, when they push the block forward, the block pushes them backwards with the same force. I don't have a picture of this, but when you're swimming, you're basically doing the same thing. You're taking your hand, you're basically cupping a bunch of water, and then you're pushing the water backwards in order to propel yourself forward. So the action is you push the water back, and the reaction is that the water pushes you forward. Um, I also want to go back to the walking. This can actually also be seen for anyone who skateboards. When you skateboard, the way that you propel yourself forward is by pushing the ground back. The harder you push back, the faster you go forward, because when you push the ground back, the ground pushes you forward. Planes and balloons and all these things basically also work the same way. That you end up expelling something in one direction in order to propel yourself forward. So Newton's third law, like I said, is overarching. It pretty much covers a wide variety of stuff. Despite the fact that it is so simplistic, it actually carries a tremendous amount of importance compared to some of the other laws. Uh, yeah. Now, this is also the reason of gun recoils. So if you've ever seen it in movies, or if you've ever shot a gun, you may have known that when you shoot a gun, the gun ends up flying backwards from the recoil. And basically, this is a perfect example of Newton's third law in action. When the gun shoots the bullet is experiencing a force pushing it out of the barrel. But that same force that pushes the bullet forward ends up pushing the gun backwards as well. The faster the bullet goes, or the more force that's required to propel the bullet forward, the more force is going to come back on the gun. So with a lot of these guns, you'll notice is that they're all fairly big and powerful guns. This is a very powerful revolver. Some of these are rifles and shotguns. So they're going to end up having a really powerful kickback due to the fact that the bullet ends up experiencing a very strong force within the barrel. I don't have a little image of this, but typically the way it works is that there's a gas within the gun that basically expands out, pushes the bullet forward, and then it expands and pushes the gun backwards. So inside the barrel of the gun is a expanding gas that pushes on all sides, and that's what's causing that kickback on the gun. You could find a bunch of videos that are like this. Going back to the whole idea about Newton's third law, it's also one of the reasons why if you try to punch something, you'll end up feeling a lot of pain in your hand afterwards. Because again, when you punch a wall, let's say, that wall is punching you back with the same force. In fact, it's very common that when people get into fights, they end up resulting in their hands being bruised, bloodied, or even broken due to the fact that every time they punch forward, that whatever they're punching, if it's a person's arm or face or, like I said, a wall or some other inanimate object, that object is pushing with the exact same force onto their hands. You can watch all these video clips of funny people being surprised by the kickback. Another thing to point out is that this also explains troll logic. So you might have seen pictures like this online or something very similar that basically shows, oh, we can get these really nifty effects if we take advantage of magnets, like putting a magnet in front of the car so that it attracts the car forward, or using a magnet to propel a car upwards, whatever it is. But the problem is that Newton's third law tells us that this won't work out. So first off, we have two forces. Not only is the magnet attracting this metal plate forward, but the metal plate also attracts the magnet backward. Now, as I mentioned before, if these are two separate objects, like in the case with two objects connected by a spring, then one of them, this car would only feel the forward force, this magnet only feels the backward force. So the car would experience a forward motion. But notice how the car is connected to the magnet. That means that this is one single object. So when the car pulls forward and the magnet pulls back, that is an equal and opposite reaction force. So combining this with Newton's first law, this will tell me that the two forces end up canceling out and the object will remain at rest. The same thing with here, putting a magnet above another magnet. Once again, they're going to be attracting each other with the same force, equal and opposite. And because it is once again connected to the car, then I won't get any net effort. If, on the other hand, the magnet was actually connected to the ground and stationary, then it would result in the car moving forward because these are now two separated objects that are allowed to move differently. One only feels a force going forward. The other one feels a force going back. So I just wanted to point that out. In fact, that's actually how maglev trains work: is having magnets on the ground that propel you forward in a similar way. But because the magnets are stationary or somewhat stationary, uh, we end up having the only one object experiencing a force. It's not something like this where it's connected to the object. So I just wanted to point this out. Now, it is important to note that while the forces are the same, the effects from the forces will be different. So going back to the whole gun situation, when a person shoots a gun, uh, both the bullet and the gun feel the exact same force, but one of them is going to experience that force differently. Because of the bullet's low mass, it's going to feel a much greater acceleration. So this is how we combine Newton's third law with Newton's second law. So if we say the force from the bullet is the same as the force from the gun, we can see that since the gun has a much bigger mass, it's going to have a small acceleration. For the bullet, it's got a small mass, which means it's going to have a high acceleration because of the whole everything has to be balanced on both sides. So decreasing the mass while keeping the force the same will result in the acceleration being much higher. This is why when a bug hits a bus, a bus is driving by, hits into a fly that's on the road, uh, they both feel the same force because of Newton's third law, but one of them feels so much acceleration it literally explodes because its body can't handle the acceleration, while the other one barely even notices. So uh, a lot of people tend to, this is actually the big issue with Newton's third law, is that a lot of people will mistakenly think about the effect of the force and think about what's going on with the acceleration instead of thinking about the forces themselves. So the forces are always the same, but the effect from the force is going to be different. And the effect or the acceleration is going to be dependent on the mass. From Newton's second law, the lower the mass, the greater the acceleration. So here are some practice questions. Pause the video, work itself, and we'll go in a second. All right. So these first few questions, they're really basic. They're just kind of more like the tricky questions that they kind of slide in there. Again, these are strictly Newton's third law questions. The type of questions that you're going to be seeing later on, uh, I'll be covering them a lot more in the multi-mass system, since that's where it's going to become a lot more useful. But Newton's third law is going to basically act as a stepping stone to answering the questions. But these first few questions that we're going to do, very basic because they're just Newton's third law. And there's really not much you can do with just the third law. So for here, they tell us that they want us to compare the forces that the stroller exerts on the man versus the man exerting on the stroller. And the whole idea is that it's the same. Again, Newton's third law says that for every action, there's an equal and opposite reaction. If the man pushes the stroller with a force of 5 newtons, the stroller pushes the man with the exact same force. Number 15, pause the video, work itself, one more second. So this is actually a little bit more similar to how you can start using this. Obviously, this is still on the easier end, but here we have a scenario where we have a spring attached to two cars. We know that one of the cars experiences a force of 1 newton. If I want to know what the force is on the other car, because of Newton's third law, it's got to be the same. Now, a nice way to expand on this question, I can follow up and start talking about what is the acceleration on card 2, or the 2 kilogram card. And by knowing that the forces will be the same, I can then uh, continue with this and do extra calculations. But that ends up being like the key factor, that the forces are the same. Here's the next one. Pause the video, work stuff. I'll move in a second. All right. Once again, this is a Newton's third law question. If the Earth exerts a force of F on the Moon, then the Moon exerts the exact same force on the Earth. The whole talking about the masses and how one is 81 times, that's just a red herring. It's put in there just to trick you and confuse you. It has no relation to this. Here's the last one. Pause the video, work itself, and we'll go over in a second. All right, so this is a little bit, like I said, this is a little bit similar to kind of what you would use Newton's third law in, or the way that you would use it. So they're giving us this information. We have a cannon and a cannonball being fired. They tell us what the masses are. They tell us explicitly that the cannonball feels a force of 100 newtons, and then they want the acceleration by the cannon. Well, based off of the values that they give us, we know that we have to do F net equals ma. We know what the mass of the cannon is, but the issue is I don't know what the force is on the cannon. Well, this is where Newton's third law comes in and where I go, okay, since the cannonball feels a force of 100, then the cannon has to feel the same force. And therefore, the acceleration on the cannon is 1 meter per second squared. Compare that to if I were to use the mass of the cannonball instead, the 20 kilograms. If I use that, I would get that the acceleration is 5 meters per second squared. So again, both of these are going to feel different accelerations because they're different masses, but the force they experience is the same. Knowing what variable is the same in order to link these two scenarios is very crucial. All right, so that's pretty much it when it comes to Newton's laws. Now, there is actually one last thing that I want to say. Normally, I just kind of recap in this section, but I want to remind you of what your expectations are when it comes to these laws. Now, I kind of briefly went through the physical, sciencey definition of the laws because you don't really need to know the laws verbatim. You don't need them word for word, even though most of you should already know what the laws are, like I said, from other science classes. However, the important thing that you need to take away from this is you need to know the spirit of the law. You need to know what the first law is referring to, the second, and the third law. The reason being is that when you're answering questions on the AP, free response questions, where you have to provide an explanation, the way the AP grades stuff is they grade it based off of a checklist. So the graders are given a checklist of, give a student 1 point if they say this, give a student 1 point if they say that. One thing that they really harp on the AP grading is that you make sure that you are explicit in the information that you provide. A good example of this is if you're doing a question where, let's say, the question is something like, how do you know that the forces have to be the same? Or how can you figure out what this force is? If you just say the forces will be the same, they won't fully grade that. They would say that you're missing some information because you weren't being explicit as to why they have to be the same. So one thing that they would look for is you making a comment of which specific law are you using in your reasoning. We haven't done laws yet. This is kind of the first set of laws that we've talked about. We'll be doing more laws later on. But this is one of the things that you have to try to get in the habit of doing, is saying, due to Newton's first law, due to Newton's second law, we know this. Therefore, this is going to be true. So if you're doing a problem where you have to explain how we know that a force going to the right is greater than the force going to the left, what you'd have to say is, due to Newton's first law, one thing that you could say is, due to Newton's first law, we know that since an object is accelerating, the forces have to be unbalanced. Therefore, one of the forces has to be greater than the other. And due to Newton's second law, whatever direction the acceleration and force act in the same direction. Therefore, if it accelerates to the right, the force to the right is greater. So you need to make sure that you're making comments like that. you can't just say, oh, this is true, and assume that the person grading understands that you are referencing a certain law. You have to be very explicit and say which specific law you're using. So just try to get into that habit. And like I said, that's really all you need to know about the laws. Like they're really major. We're constantly going to be using them. In fact, in the future, there's only like one more equation in this topic that we're going to learn. But for the most part, we're going to be constantly going back to F net equals MA, FG equals MG, and just the idea of the two other laws. So you want to make sure that you understand the spirit and the meaning behind the laws. And you can identify, oh, this is a Newton's second law question, or oh, this is a Newton's third law scenario. All right, that's pretty much it. Like I said, we'll kind of return back to Newton's third law later on when we get to the multi-mass systems, because that's going to be where we're dealing a lot more with interactions. If you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.